First, we want to look at the case of pendulums being simple harmonic motion. To do that, we said that simple harmonic motion is something that follows Hooke's law. So let's see how Hooke's law could possibly relate to pendulums. So here we have a pendulum swinging back and forth through this angle. So it's going to swing back and forth like this. We have some arc length S that it's going to follow. We have the angle that it's going to go through. And if we plot a free body diagram here, we have tension pulling this way, gravity as always pulling straight down. And we could split it into components, kind of similar to what we would do on a ramp, even though that angle there is always going to be changing. And what's pulling it back towards the center is mg sine theta. So when we think about Hooke's law, right, force equals negative kx, we said it's a restoring force. It's always pulling back towards the center. Well, that's true for this x component of gravity. This component right here of gravity is always pulling it back towards the middle. So let's start by taking a look at that part of gravity. So if F is going to be negative mg sine theta, we want to see how that matches up to Hooke's law. Well, for small angles, and by that we mean less than 15 degrees, theta is approximately equal to the sine of theta. So for small angles, we can rewrite this as F equals negative mg theta. So that's a good start. We also know from some of our circular motion stuff that theta is equal to our arc length divided by the radius, or in this case, the length of our pendulum. So we could write this as F equals negative mg s over L, and kind of rearrange the way we write this and say negative mg over L times s. And now we have something that's somewhat similar to Hooke's law up here, kx, where this mg over L is essentially our value for k, and s is essentially our delta x. So we have F equals, its own way, negative k times x. So for small angles, because remember we had to make this assumption up here, pendulums do follow Hooke's law, and so they are simple harmonic motion. So we think of period of a pendulum, we want to think of period of any simple harmonic oscillator, 2 pi square root m over k. And remember from our last derivation that we came up with the fact that for a pendulum, k was essentially mg over L. So let's go ahead and replace that in our equation and say that for a pendulum, t equals 2 pi square root m over mg over L. Our masses are going to cancel, and so we're left with t equals 2 pi square root 1 over g over L. And then we could make that a little bit neater by saying 2 pi square root L over g. And that's going to be period of our pendulum. So notice period of a pendulum depends on two things: how long the pendulum is and the acceleration of gravity at its particular location. In fact, as we'll see in a couple examples, this acceleration of gravity, g, varies a little bit on the surface of the Earth, and by measuring the period of a pendulum accurately, which isn't too hard to do, you can actually figure out exactly what g is at that particular location on Earth. And you could figure it out for other planets as well. We could also think about frequency for a pendulum. Remember, frequency is just the inverse of period, so it'd be 1 over 2 pi square root of g over L, and those would be our two equations for a pendulum. So here's an example of where you can use a pendulum to figure out the acceleration of gravity. Notice first just the number of significant figures we're given here. We're being very accurate here, and that's because we're going to measure very minor variations in the acceleration of gravity. So we want to have quite a few significant digits to work with. So period equals 2 pi square root L over g is our equation for a pendulum. We want to solve here for the acceleration of gravity. So first thing, we're going to take t divided by 2 pi equals square root of L over g. Don't forget, when you put this in your calculator, make sure you have a parentheses there. Common mistake to avoid. And so we're going to square that to get rid of our square root. So t over 2 pi squared equals L over g. And then we could multiply both sides by g to get rid of our fraction, and then divide that way, and end up with g equals L times 2 pi over t squared. So when we go to solve for g is going to equal our length of our 75 centimeters, or 0.75000 meters, times 2 pi over our period, 1.7357 seconds squared. And the acceleration of gravity we get, carried out to 5 significant figures, since that's what we have up in the problem, would be 9.8281 meters per second squared. That's our final answer.